Okay, good morning, everybody. Pray be to the Lord.
Forever.
Okay, guys, we're going to continue with our reviews because all this week are going to be review. And we're going to talk about, remember, the topic of forces and motion. And also, we're going to remember the three laws of motion from Sir Isaac Newton. So please pay attention. If you have any question, make it. Okay, you have the opportunity to make a question about the topic, obviously, right? So, we're going to continue actually with let's see. Just give me a minute. So, please pay attention. As I tell you, if you have any question, please make it. Right, about the topic about forces and motion and about the three laws of motion from Sir Isaac Newton, right? So please, let's see this one. Where is the video? This one. Pay attention.
What is force? Let me tell you what you will probably read in your textbooks. Force is a push or pull upon an object, right? Though this cannot be really classified as incorrect, it hardly explains anything about the concept of force. This is what you will assume after reading this definition. You will imagine a stationary object on the ground and someone pushing it or pulling it. Yes, when force is applied, the stationary object will move. But just this does not explain the concept of force entirely. Before we move on to the definition of force, let's clear a few misconceptions about it. Let me ask you a question. This ball is lying at rest on the ground. It's stationary, not moving at all. Is there any force acting on it? Listen to my question carefully. Are there any forces acting on the ball when it is stationary? If your answer was a no, or if you didn't have an answer, it means you don't know the concept of force yet. The answer is yes. There are forces acting on this ball. There is a gravitational force which is trying to pull the ball towards the center of the earth. And the ground is applying an equal force exactly in the opposite direction. This force is called the normal force. Because these two forces are balanced, they do not change the position of an object. The net force acting on the ball is zero. So what does this tell you? Just humans pushing or pulling is not the only kind of force. And just because there are forces acting on an object will not mean the object will move. For the object to move, there has to be some net force. So now let's say a person softly kicks the ball. What happens then? Yes, the position of the ball changes. Why did the position change? It's because there was another magnitude of force acting on it, and this time the forces were not balanced. The ball moved and there was displacement. But hold on, why did the ball stop moving after covering 15 meters? The ball started moving at a pace and then slowly came to a halt. If there's no force from the other side to stop it, how did it stop? Was there a force which stopped it? Yes, it was friction that stopped the ball. While the force you applied was towards the right, the force of friction was towards the left. Let's make it even more interesting. Assume your screen to be your frame of reference in this example. Also assume that this straight horizontal line is a frictionless floor and there's no air resistance. The ball appears from the left of your screen and moving towards the right at a uniform velocity of 2 meters per second. The only two forces acting on the ball are the gravitational and the normal forces which net each other out. In this setting, will the ball ever stop moving? No, it won't. It will continue to move along the same path at the same speed unless there is another external force which acts on it. Here, as the forces are balanced, the ball will continue to move at 2 meters per second. Most people assume that if the object is moving, then there is some net force acting on it, but that's not true. An object will continue to move at uniform velocity even if the net force on it is zero. So there are two things we've learned here. First, if the object is stationary and the net force acting on it is zero, then it will continue to remain at rest. Second, if the object is moving at uniform velocity and the net force acting on it is zero, then it will continue to move at that same uniform velocity. Now, when this ball is moving at 2 meters per second and there is an external force applied from the left, what will happen? Yes, the ball will accelerate. Its velocity will change. Let's say the velocity changes to 3 meters per second after this external force is applied. After that, the ball will continue to move at 3 meters per second unless acted upon by another external force. So nobody's really seen or touched force. It can only be understood by knowing what happens to an object when force is applied to it. If the body is stationary, do not assume that there is no force acting on it. And if the body is in uniform motion, do not assume that there is some net force acting on it. So what is force? A force is a push or a pull upon an object resulting from its interaction with another object. So when you kick the ball also exerts some force onto your leg. But as the force of your kick is stronger, the ball moves to the right. There are many more concepts we need to understand about force, which we will cover in the next video.
Please watch the second video about what is force in part 2. Then we're going to see the laws
In the
of
first
Isaac
part,
Newton.
we saw that force is not just a human pushing or pulling an object. A force is a push or pull upon an object resulting from its interaction with another object. There are two things we will cover in this video: types of forces and the effects of forces. For simplicity, we can classify forces into two types: contact forces and non-contact forces. Contact forces are just what they sound like: forces that result from the interaction of two objects in contact with each other. Are there any contact forces you know of? Of course you know a few. What happens when you softly kick the ball which is lying on the ground? You applied a force on the ball and there was contact. Applied force is one of the contact forces. Next, there is a force of friction which brings the ball to a halt. As the ball is in contact with the ground, the frictional force is also a contact force. Don't you think there was some air resistance? Yes, air resistance too is a contact force. The normal force, which is applying force in the upward direction, is a contact force as well. These were some of the contact forces we know of, but these are not the only ones. Can you think of any non-contact force? What happens when the ball is in the air? It will fall down, right? What pulls the ball down? Yes, it's the gravitational pull which is trying to pull the ball towards the center of the earth. This pull happens even if the object is not in physical contact with the earth. The gravitational force is an example of a non-contact force. Other examples of non-contact forces are electrical and magnetic forces. Now, I want you to think about the next question I'm going to ask you. What all can a force do? What can be its effects? Let me give an example. A force can set a stationary object in motion. That's one of the things force can do. Can you think of the other things it can do? Assume an object is moving at a uniform velocity of 2 meters per second. If it is pushed harder, its velocity will increase. So force can also change the velocity of an object. A force can also stop a moving object. Anything else you can think of? Yes, force can also change the direction of a moving object. If a ball is moving towards the north, a kick from the right can change its direction to northwest. Is there anything else you can think of force can do? Come on, I want you to think really hard. Don't think only in terms of motion. A force can also change the shape of an object. If we apply force from both sides to a spherical ball, its shape changes. The ball's position does not change, but its shape does. So these are some of the things that force can do. In the next video, We will play an interesting game to know if you've really understood how forces act on an object.
Okay, guys, so to continue with our review, we're going to watch the three laws of motion from Sir Isaac Newton. Do you remember when you write the biography of Sir Isaac Newton about how he discovered the one of the laws that is gravity and the other ones that you will remember in the um, in the videos that I really prepare for you. Then we're going to review from the book just some parts, important parts from the book, and we finish with our review for science.
Imagine you're sitting on a recliner chair watching your favorite movie on a lazy Sunday. And your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you're practicing for your 100 meters race on this track, and somebody asks you to stop immediately within a second. Will you be able to do it? What if you're suddenly asked to turn towards the right? Will you be able to turn immediately? The answer to both the questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it's at rest, it will remain at rest. And if it's in motion, it will stay in motion. But what can change this? Yes, only an unbalanced force can change this. If it's at rest and an unbalanced force acts on it, it will move. If it's in constant motion and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. Here's the correct definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. In simple words, it means that the objects continue to do what they're doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If the forces are balanced, there can be two cases. An object may be at rest, or an object will be in motion at a non-zero constant velocity in a particular direction. These can be the only two cases when the forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. In the next video, we will look at a few applications of the first law of motion. Do you remember the Newton's first law of motion? It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced, only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let me ask you a question, and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, let's say there's an object on a table. You apply a net force of 10 units on it, and then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? Surely it's the 3 kg one because it has lesser mass. Lesser the mass, more the acceleration. And more the mass, lesser the acceleration. Hence, we can say that acceleration depends inversely on the object's mass. If you understand this concept well, then understanding the second law of motion will be very easy. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared. The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table and the subject exerts an upward force on the object. There are two forces that result from this interaction, a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right. It exerts a forward force on the bullet. And the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration. Or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
Okay, guys, we already saw again the 4 videos about force and motion, about the 3 laws of motion, about Sir Isaac Newton. Okay, but if you remember, let's go on page number 60 in our book. Page 60, right? And we're going to remember about what are forces actually. If you remember, forces is a push or pull that acts on an object. It's like you push, just push, and that's it, only push, right? Push, that's it, yeah, that one, push, 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 yeah, that too. Okay, so that is the force. The force is you put in an object, push, that's it, right? That is, yes, it's only that. It's you, if is the way if you have a ball that we saw in the video. No, not that kind of push, Fatima. It's is if you have an object, in this case a ball, or you kick it, or you only push, and that's it. That is the force you put in an object, just to push. Okay, that is a force. We have two kind of forces. If you remember, we have contact force and we have non-contact force. Contact force, to remember, is when require two pieces of matter to touch it. For example, the ball. I will make it with the ball again. If you push the ball, yes. If you push the ball, you contact the ball. You have to touch it to the ball start to move. Right? That is a contact force. Also, it depends in the force you use. It depends the force you use to move the ball. Okay, and in non-contact force, for example, if I use my fan in here and I use a piece of paper, look what is going to happen. I have my fan in here. In here, I have my fan. This is the thing that happened, right? I'm not using a force. I'm not using nothing to start to move the paper. This is non-contact force, actually, right? What is non-contact force? Is when an object is pushing or pulling and not touching the object being pushed or pulled. A force that acts a distance is called a non-contact force. What I'm using in here? Air. I'm using air. The air, I'm not touching nothing, and the air is pulling the paper. This is a non-contact force, right? Right? Do you have any questions still now? No. Okay, very good. Now, also we have gravity, right? Remember, gravity um, is the force of attraction, right? Is the force of attraction between any two objects. That is gravity. For example, I use this. This is heavier. I'm use this. This is attraction, right? This one. Why? The cell phone is attracted to my hand, not the meaning, not in the way of the meaning that my hand have a gravity, right? No. Remember, the Earth have a point of attraction that is the nucleus, and that is the gravity. Si usted se tira de cualquier lado, usted se cae del suelo y la gravedad fue la que funcionó, right? Eso sí, le va a doler, right? So, to continue with the laws, the Newton's laws, we remember the first Newton law is what? What is the first Newton law that we saw in the video or in the videos?
An object will still moving unless an external force acts on it.
Yes, but that is one, that something have a name. What is the name of that law? That is inertia, people. Remember that. The Newton first law of motion says that an object will stay in uniform motion unless a net force acts on the object. Without a force, an object at rest will stay at rest. The meaning is, if you, for example, with a ball, if you don't push the ball, right, the ball will stay in there, in that place, doesn't move, don't move in any place, because you don't use push, right? Or you don't use the force of pushing the ball. That is the first one. It's inertia, the first one. The second law of motion. What do you remember? What is the second law of motion?
Mass times acceleration.
Exactly, very good. The second law of motion, or Newton's second law, describe how acceleration, mass, and force are related. Force is the product of mass and acceleration. Do you remember the formula, right? The force acting on an object can cause the object to speed up, slow down, or change direction. If you remember, is force, it's equal to mass times acceleration, right? That is the formula we use. And to calculate all of that, we use what? Newtons, very good. Newtons, right? And the third law of, the third Newton law. The third Newton law says, states that when an object exerts on a force on a second object, the second object exerts a force of the first. For example, it's the same weight as inertia, but in this case, the third law means the force you use to move the object, right? For example, using the ball again. If you make a little push to the ball, the ball will move in a slow way, a short distance. But if you come strong and make a really strong push to the ball, then the ball will move faster and will move far away. It's like you play football for that religiosos who loves to play football, who believes they are Cristiano Ronaldo Messi and no llega ni a Rubilio Castillo, right? Many of you boys, boys, and some girls, isn't the way when you make a pass to the other partner of a team, you calculate the force of how to move the ball. Quítate eso de la cara, vos. Is this in the same way of the football? When you kick the ball to make a pass, you use a relative force to pass the ball. But if you want to kick the ball from the middle of the field to the goal, right? you will use more force. You will use more of your strongest in your legs. Que le salga volando el balón para otro lado, pues ya es porque usted es patudo, ¿va? Pero bueno, como un montón de que los que yo he visto jugando aquí. So, people, at 9:30 we have math. I will see you at 9:30 for math. Thank you for being here. I have 23 students. I don't know who's missing. Well, no, 22 students I have in here. Okay, I have 22 students. I don't know who else, who missing. Okay, I will see you at 9:30. Please enter to Imagine Learning and start to, I really don't, I didn't assign the playlist yet. So please work. If you have any doubt, if you have any assignment as homework, you didn't finish, you didn't send it to the platform or to email, okay? See you 9:30 math. Bye-bye.
Bye, Mister.
Hi, Mister.
Bye.
Bye, Mister.
Bye.
Bye, Mister.
Bye.
Uf, uf.